Hi, my name is Pianegonda, and today we're diving into the topic of translating product requirements into plastic requirements. So, as a first and crucial step in the plastic selection process, the requirements from the application must be documented, and uh, they sometimes need to be translated. In our Great Match framework, we provide a structured interview questionnaire that supports this, so you have everything in there from technical, regulatory, um, economic, and sustainability requirements. So you're all set there, you have a railroaded process that you can use in order to gather all the requirements. However, sometimes it is unclear what the requirements for the plastics really are, and if they are really needed. And this is the topic from today's video. For example, if we have requirements like, it needs to be soft. Yeah, that translates to some kind of shore hardness, but which shore hardness do you actually need? How soft does it have to be? Then you have, it doesn't need to break when you drop it, but what impact toughness does this relate to, translate to? It doesn't need to buckle if you have a, let's say, IOL injector or a syringe or an auto injector, stuff like that. If you push it, it doesn't have to buckle under load. What stiffness do you require in order to achieve that property? It needs to look nice. Yeah, what does nice really means? We need numbers. So if it can't have too many black spots or can't have too many streaks, you have to define what is acceptable and what is not acceptable. Because zero tolerance is basically unachievable. So, and therefore you need to define what is acceptable and what's not acceptable. And it needs to be high quality. Yeah, the question is what quality really means. Does that mean that it is like it feels heavy in your hands? It feels that it's worth something, or does it mean that it looks nice? Yeah, so it doesn't have too many black spots, or it doesn't have too many flashes. Define what quality means to you. Then are all these requirements are pretty vague, and they need to be translated into concrete plastic examples, plastic requirements, excuse me. And here we want to give you a tool to translate these into measurable, verifiable requirements. But first, let's challenge the requirements, because it is crucial for the CO2 footprint and the cost of a medical device to not be over-engineered. And over-engineering very, very often starts with the requirements. So you just put a lot of requirements in there, you never challenge them, and then you have to fulfill all of them, and then you over-engineer what your device is actually supposed to do. Challenging them, therefore, is imperative in order to reduce your CO2 footprint and your and your cost. So I can't stress that enough. If you don't challenge your requirements, you will over-engineer your product and therefore have them cost too much and have them have too much environmental impact. Never accept the following reasonings. The customer wants it like this. We always done it like this. This is my favorite. And regulatory requirements as an answer. You always have to dig deep into the origin of these requirements and find the source. The primary source where the requirement is coming from. For example, the MDR. Go look at which article or which part of the annex this requirement really is coming from. Read the words and verify that this is really a requirement that is applicable to this kind of, let's say, device. If you cannot find the source, there is no requirement. It's just as easy as that. And don't let opinions be your requirements. This cannot be made from, so let's have some examples. This cannot be made from recycled material. Okay, how do you know that? This is you, in parentheses or in this cannot be made from recycled material is like your product manager or whoever is telling you this. Okay, how do you know that? Because of regulatory requirements. Okay, which ones? Yeah, the MDR, it is in the MDR. Okay, where does the MDR mention that? And then you either get two responses. Number one is I don't know. You cannot accept I don't know. I should be adding this up there. But you cannot accept I don't know, because if you don't know where the requirements are coming from, how do you know they are true? You cannot know they're true. So what you need to force them to do, or you need to force yourself to do, is read the full text. And then it doesn't mention that recycled materials cannot be used. It just says that materials have to be safe and effective. So the question is, how do we make sure that our recycled plastic is safe and effective? And that's the real challenge. And then you can go into all kinds of quality and risk management measures. We will dive into that in the later stages of the program. But this is actually the requirement: safe and effective. Yeah, duh. Medical devices have to be safe and effective. Who thought? Good. So we could debunk that. We will not accept this requirement. Then the housing part needs to be V0. Yeah, everybody uses V0 for housing parts. How do you know that? Yeah, because of the regulatory requirements. Okay, which ones? Yeah, it's the IEC 6061-1 standard. That is safety for electric and electronic medical devices. It's like 500 pages or something. It's like the MDR is a child's play against this. Good. Where does it mention that? Now, either you get I don't know, which you cannot accept, and then you can have it read the full text. Oh, it doesn't mention V0. It only mentions V1 at maximum, or V2. Okay, we will take V1 then. So we downplayed this. I wouldn't say we deleted it completely. There needs to be some kind of flame retardancy in an electronic medical device. But going to V0 makes your material selection process much easier, and you do not use as much flame retardant. So you start to get the idea. This must look nice, look premium. How do you know that? Because the customer wants it like this. Okay, how do you know it's important to the customer? Here it's gonna be very important. I flipped the script a little, and because color and appearance clearly influences their buying behavior. Okay, we might be onto something. Okay, how do you know they buy the product because of the look? It's like we have a survey that clearly indicates that it would be that the customer would prefer a product with good looks. On top of that, we once changed the color from white to off-white due to cost reasons, and the sales dropped by 20%. Okay, we're gonna take this requirement. It needs to look nice and premium because it clearly influences the customer behavior. Customer is always right in terms of taste, You know, there's the full quote. Not the customer is always right. The customer is always right in the matters of taste. But not to get sidetracked, we could verify this requirement. So coming back or summarizing, never accept I don't know as an answer. I don't know means your requirements are an opinion. Opinions must not be requirements. You cannot accept that opinions are requirements. Either the requirements can be properly argued for or they get deleted. Very easy. Now, it is not always easy to challenge decision makers on their requirements and their opinions. So what you have to use is something that we call belief-breaking questions. So that is okay, how do you know that? is that's much better and much less offensive to people than why? Why would you do that? Why is always an assault, basically, a verbal assault. To be a little exaggerating here, but it's like, how do you know that is much more, let's say, smoother, and it's a so-called calibrated question. You ask them something, you know what you want to hear from them, but they need to formulate it themselves, otherwise they will not accept it as the truth. That's very important. So what you can do here is you can read Never Split the Difference from Chris Voss. He's a FBI hostage negotiator and now has a consultancy on how to negotiate. And like these calibrated questions is one of the key resource or the key tools he uses in order to get people to think what he wants them to think, or to get them to a conclusion that he wants them to take. So it's basically a Jedi mind trick. You can call it manipulative, but it's the best negotiating tool that you have. Open-ended questions that are calibrated to get what you want. How do you know it's true? And sometimes they know it's true and they can prove it to you, and then you should accept that. It's not about getting rid of all the requirements, it's just getting rid of the unnecessary ones. Never argue, only question. Let them arrive at the conclusion themselves. It's very important. If you cannot do that, you will not get rid of the requirements. It's just like, because I said so. And you have to avoid because I said so at all costs by using questions. So then now we're getting into the translating tool, and now we're getting into the weeds. How something can be verified defines your requirement. Let me repeat that. How we can verify something defines your requirements. That's the most important point. That's what a requirement means. You gather the requirements as it is, like has to be soft, and then you think about, how would I verify that? So I could, for example, order samples, sample plaques. So you just like small pieces of the rubber or small pieces of the thermoplastic elastomer, and then give it to whoever decides what soft enough is. And then they can decide, yeah, I like this one. And you can also do prototypes and do testing. So if you have like an applicator or something, then you mold a bunch of different shore hardnesses, and then you try to applicate something, and then some work, some do not. Or you can also say, okay, let's apply a rating. We have shore A10, which is gonna be the best. It's very soft, extremely soft. And then we have a shore A hardness 90, which is basically a tire. So hard rubber. And then that is basically your rating scale. That's a 0. So if you want it to be as soft as possible, you can just say, yeah, every material who has like the softest shore hardness, that's gonna have the best points. So it's gonna get more points for better or lower shore hardness. Then we rate these verification methods, and we also have to challenge them. So I think one thing is missing here that I need to add. It's like we need to rate them, the verification methods, in terms of time, in terms of cost, and in terms of effectiveness of getting at the right product property. And if you look at these 3 examples, you have the order the sample plaques. Like I like this one. It's a little time consuming, doesn't cost you much because you need to order the samples, and that takes a few weeks usually. But it's not really effective at doing what you want it to do. It's like, I like it the best. It's not very a very reliable measure of achieving your goal. And then make prototypes. Yeah, that costs you a lot, or like the most. It's not very expensive, but it costs you something. It takes more time than everything, but it's also very effective at achieving your prototyping goals. You probably also need to verify a lot of other requirements, but just in terms of material selection, you try to avoid prototyping before you like make a material recommendation, because that's like your first step. You get a material recommendation, then you go into sampling, prototyping anyways. So what I would do is you apply a rating and say the lowest shore A hardness is gonna get the most points, and the higher the shore hardness, the less points the material is gonna get. And then with that we go into material recommendation, and then we start prototyping after that, and then see if it works. And we still have option B, C, D that we can go into and use for prototyping. And then at the end, we will apply the best verification method and therefore define the requirements according to this verification method. And let's just, I'm just gonna pull up a sheet, which is a resource I'm gonna provide to you. So we are going to start with as is vague requirement needs to be soft. First we challenge it. That's always the first step. We challenge it, and then we can like, okay, it needs to be soft. We can basically delete that because we could challenge that. Or I mean, if we cannot challenge it away, we translate it. So we go with the first verification method, and it's that samples, and then we say prototypes, and then the last one is rating. So it's if we have cost, yeah, sample is like doesn't really cost much, so it gets an 8. We always rate from 1 to 10. That's like the easiest. And then time wise, it's probably a 6, and so score is 14. Very easy. Then we have cost in prototypes. It's probably a 4. It doesn't cost you too much, but it costs you something. And time is probably a 4 also, so it gets a score of 8. And then cost and for the rating, that's like a 10. And the time for a rating, that's also a 10. So you should be applying basically this. You could add, and I'm probably later gonna do that, verification method effectiveness. And then you rate the effectiveness on, yeah, how effective is that at really getting to the product requirements that I really want. So that's a good thing. I will update that. Good. So we have this resource and we translated it, and now we have to talk about verification methods or methods of verification. Verification can actually be done by 3 different methods or sources. Number 1 is literature and documentation. So you request a technical data sheet, you request a certificate, something like that from the supplier, and there's just like, yeah, we can do this. And it's just a confirmation. Then we have a test by proxy, what I call it. Is that can be prototyping, that can be making product-like samples, but it's not a material test, basically. And you can do also prototyping tests. That's not right. Okay, you can test by proxy, which is prototyping tests, and then you can also do material tests, which means you can either test at a material or you can test at a prototype. So that should be by proxy. Let's just quickly change that if we have it. Excuse me. As you see, we're building, we're improving. So what I'm just gonna add is like a material test. So see, and now we're gonna do from current slide. Let's just go back. See, material test by proxy, which could be prototyping when we just want to add that prototyping. e.g. can be prototyping. Good. And let's go there. Verification on the paper basis, meaning documentation and literature, should usually be preferred to running tests. It saves money, it saves time, it saves effort, and the faster you can develop a medical product, the cheaper it's going to be in terms of development and development cost. And your whole regulatory pathway will take up a lot of time. The whole biological testing, clinical evaluation, and let's say approval is gonna take you a lot of time. So time to market is always an issue. Therefore, doing a lot of material tests, doing a lot of prototyping slows down your process. You should always try to verify and make a minimal viable product. That is true. However, for material selection, you need to, as fast as possible, come to your recommendation and then go into testing. Then go into testing when you have evaluated the material as best as possible. This all sounds a little bit theoretical, but examples make this much more clear. So we have degrees of verification, and that is the first thing we have to also talk about before we come to the examples. How do I know my plastic choice is gonna be 100% perfect? How do you know that? That's the neat part. You don't. So it's always the question is how much can you fulfill the requirement? And some requirements, they are Boolean, yes or no. So does it comply to REACH? Does it comply to ROS? Yes, no. But even there, does it comply to REACH? Yes, it complies to REACH, but it has an SVHC in it. You comply if you give them all the information they need. So if you basically tell them that you have this substance in there, you are fulfilling the requirements. But so it's not really a true or false. It's like, is it above? Does it have a stiffness above 2,500 megapascals? Yes, you can. But how much? Value based. You can also have value based. Delta X over certain requirements. So we need at least 2,500. We have 3,000, so we have 500 as a spare. Do you need 10,000? Probably not, but it's enough. It's a lot stiffer and not better, so you could probably have other advantages there. Or you can have a rating. You can say it's like a 0 to 10. Good example for that will come later. So we have an example requirement here that we're gonna take apart. Is a plunger has not to buckle under load. So how can we verify that, and how can we explain degrees of fulfillment, of requirement fulfillment at this plunger? We have different approaches that we can take. Number one is we can test by proxy. We mold a plunger, assemble a prototype, test this under real load, and then see if it buckles. It's like very, very low tech approach. You just do the thing and see if it works. Trial and error. Approach number two, we simulate. We simulate a model under assumed forces and calculate the needed stiffness for buckling. So this is a high-tech approach. You need some knowledge about how to do FEM calculations, but it's gonna give you a number for stiffness, and then you can select the material according to this number of stiffness. And then is an approach that I call experience heuristic. Heuristic is a shortcut, mental shortcut or rule of thumb. So we know that previous products had plastic grade X, and that's plastic grade X that works, and therefore we know that if our grade that we're going to select has a stiffness of at least the reference grade, it will not buckle. So I know this works, therefore if it's stiffer or at least as stiffer as this, it will work. Good. So we can now go ahead and summarize this. So we have the test by proxy. We're going to assemble a prototype, and it's pass or fail. It's a Boolean, yes or no. Simplicity, it's very simple. Then first time right probability, it's a gamble. We don't know if it's gonna work or not the first time that we sample, so they're slow. Then we have the potential for over-engineering. We don't have a very high potential for over-engineering unless we start with something that is extremely stiff at the beginning, and then it will work, and then we will be sitting there. So probably it's a medium. Probably I should change that to medium. Yeah, let's change that to medium. Medium. So cool. And then the ability to verify on paper, none. That's basically, that's basically not the name of the game. You do not verify by paper, you just try it and then it works or it doesn't. Simulation. You will simulate the plunger and the simulation says 2,500 megapascal will work. Otherwise it's gonna buckle with, of course, a little degree of security there. Margin of safety is it's called. Yeah, it's not very simple. You need a lot of knowledge in FEM calculation, how to draw your parts, etc. It's the first time right probability is very high. If you know how to do calculation properly, nowadays it's gonna be very good. And then the potential for over-engineering is low because you just do what you need to achieve your goal and more. And the ability to verify on paper is very high. So if you have simulation in-house, and that's clear from this evaluation, simulation should always be preferred before you do the other two approaches. But sometimes you just don't have that ability. There are service providers, and if you don't know one, you can always contact a coach. They will help you set up something with the simulation provider, because this can also be bought as a service. Then if you have an experience with another plastic rate, you can always use that as a reference. And so we know that our current material has 3,500 megapascal, and that will certainly work. So it's very simple. We know that we're going to get it right because if we have 3.5 megapascal and we, from the simulation now, that's a little looking behind the curtain, we know this 2,500 will work. So we will have a very high first time right probability. But we're going to over-engineer. We're going to have a material that is too stiff for what it's actually supposed to do. And you have the ability to verify it on paper. So here we have the potential for over-engineering. And as I said before, over-engineering will contribute to cost and will contribute to your CO2 footprint. So this needs to be avoided. Sometimes it's a useful tool to have it in your belt, depending on the cost and environmental implication of that specific part. So coming back to the last example, what would be a good rating, gradual fulfillment example? That would be price of CO2 footprint, because the best gets a 10, the worst gets a 0, and everything in between is gonna get the linear rating. That's a good example how you use the rating. Yeah, good. Then coming to the final verification. There are some properties that suppliers or literature will simply not be having, that are not available. And that can be climate test. I'm not talking about climate change here. I'm talking about how much heat and humidity can your material, your device handle, such as like 80 degrees, 90% relative humidity, stuff like that. Chemical resistance to certain fluids or aging data is often not available. And therefore some tests cannot be avoided. And in the end, the final verification and the suitability of a device has always to be tested and verified at the final medical device, including all processes, including sterilization, packaging, etc. So meaning that you can always do so much with the material evaluation. You cannot perfectly tell if your material is going to be the 100% the right choice. Pre-verification using supplier documents and literature as much as possible helps you speed up the development process, and boots are not replaceable for final product tests and verification. So there are no replacement for that. You need to do the final tests. The grade match framework will only help you ensure that the least amount of uncertainty will remain in your plastic choice. So you did as best as you can, the best I can do, or the best we can do, to make sure that the plastic is qualified or is the best choice for this material, for this device. And we cannot 100% ensure that. We can just minimize the probability that something adverse or something will happen that we do not anticipate. So that was half an hour. Next up will be gathering plastic data. Stay tuned for that. Thank you very much for listening. This was a sneak peek of the Great Match program and a part of the module Perfect Plastic Selection, which is the small subpart of how to translate plastic requirements. If you like the video, subscribe, give me a like, comment, whatever the algorithm likes, and have a good one.